Hello, my name is Gazan Khan. I'm a medical student and MSc graduate from the University of Manchester. I'd like to welcome you all to my talk looking at the use of AI for the segmentation of multiple sclerosis lesions. Multiple sclerosis is an autoimmune demyelinating condition that is thought to affect 2 million people worldwide. It is characterized by loss of sensory, motor, and cognitive function. MRI plays a vital role in the diagnosis and by monitoring of MS. It is able to disseminate lesions both in space and time. MS lesions appear hyperintense on T2 weighted and proton density images, whereas it appears hyperintense on T1 images. As one can imagine, the detection of these white matter lesions is a very challenging task, requiring neuroradiologists with good knowledge of neuroanatomy being able to correctly identify all pathological MS white matter lesions while also avoiding false positives. There are many mimics, such as lesions of vascular origin, that can be confused for MS white matter lesions. Furthermore, segmentation, the process by which image readers decide which voxels belong to a lesion and which do not, and subsequently delineating lesion boundaries, is a complex process complicated by partial volume effects. Ultimately, it's a long and arduous task with limited intra-reader and inter-reader variability. There has been work done looking at aims to automate the process of MS lesion segmentation. These can be broadly divided into supervised and unsupervised approaches. Supervised approaches such as convolutional neural networks, random decision tree forests, and support vector machines use pre-labeled data as a means to learn and figure out features when detecting white matter lesions, and unsupervised methods do not require any pre-labeled data. These can take the form of atlas-based approaches such as Freesurfer. Deepmedic is an example of a CNN. It is a dual pathway 11-layer deep 3D convolutional neural network which has been developed for the challenging task of brain lesion segmentation. It has shown to be particularly effective in segmenting brain tumors and stroke lesions. For this project, we aim to validate and evaluate the use of Deepmedic in segmenting MS lesions and comparing it to an atlas-based method in the form of Freesurfer. We will acquire data from the ISBI lesion segmentation challenge, thus allowing for standardized comparison and to compare other algorithms as well. The image dataset consisted of FLAIR T1 weighted T2 and proton density images that was spread across several time points for each subject. There were 2 tranches of data, a training set of 5 subjects where manual delineations were provided, and a test set of 14 subjects where manual delineations were not provided. In terms of any further pre-processing, the images were normalized to a zero mean unit variance space by myself, and binary brain masks were also generated. Below is a schematic pipeline representation of Deepmedic. 2 models were trained and validated on a Tesla V100 cloud GPU, the only difference being the use of data augmentation and additional dropout in the convolutional layers. It is believed that these overcome overfitting, a common phenomenon seen in CNNs. The model with the higher dice score was then evaluated on the test set. So, a bit about CNNs. Within CNNs, there are hidden layers known as convolutional layers, which receive data from the input layer and apply a convolution operation to transform the data using filters. These filters are specialized to detect certain patterns. So initially it can be low-level features such as an edge and a corner. When a filter is applied to an image, the convolution output will generate a strong signal output, which will be mapped onto a feature map, i.e. a representation of how well elements within the image align with the filter. CNNs generate feature maps for every filter, and these feature maps will become an input for the next layer. As the CNN progresses, more and more complex features are identified, For example, looking for nonlinear intensity relationships between neighboring voxels. A CNN has multiple layers of convolutions and activations, often interspersed between pooling layers, and trained using backpropagation and gradient descent as for standard artificial neural networks. Convolution layer is often followed by a fully connected layer that groups all feature maps together to be inputted into the final classification layer that calculates the prediction score to classify each image voxel and produce a segmentation map. As one can see, deep learning is referred to as a black box approach due to not understanding how a network reaches the decision. However, by experimenting, we can see what parameters and experimenting settings influence the performance of a deep learning algorithm. There are issues, namely that CNNs are data hungry. By that we mean a lot of data is required for training in order to perform a certain task. However, the advantage of CNNs over other image classification algorithms is that the network itself is independent from prior knowledge. It self-learns from the information provided. Here is a graphical representation of training and validation of Deepmedic. We can see by using augmentation and dropout, the model slightly improves. However, overall we can see there is marked overfitting. This is highlighted by the extremely high mean accuracy but the very low dissimilarity coefficient. Here we can see in the table that the dice similarity coefficient score for the second model, Deepmedic, with augmentation and additional dropout outperformed the original model. However, it is worth noting that the time taken to train this model was significantly increased, which is to be expected with augmentation. Here we can see in F and G the output segmentation masks from the Deepmedic during training and validation. E is the ground truth labels, and A to D are the input MRI scans. Here are the results from the test subjects. We can see Deepmedic outperforms Freesurfer as evidenced by the higher ISBI ranking score, which takes into account metrics such as dice score amongst others. However, Deepmedic compared to the other algorithms did not perform particularly well. They had dice scores in the range of 0.55 to 0.65 and ISBI ranking scores of around 90. Anything above 90 is compared to human rater level. Deepmedic was markedly worse at around about 79.586. It is worth noting that once Deepmedic has been trained, it only takes 10-20 minutes for it to segment the subjects, whereas Freesurfer took 6 hours. In terms of what the results show, we can see that Deepmedic is better than Freesurfer. However, this is only marginal in segmenting MS lesions. Overall, however, by challenge standards and including dice scores, we can see that Deepmedic did not perform particularly well. This could be primarily due to overfitting, which can be caused by the lack of training data or the overcomplex network architecture of Deepmedic itself. We did try and overcome the overfitting problem by introducing augmentation and dropout. Augmentation increases the variance of the data, and dropout simplifies the network architecture. However, this could not overcome the great effects of other architectural issues and limited training data. However, this is nothing to be disheartened by. There is evidence in the literature that shows that CNNs are effective in segmenting MS lesions, especially if given a large data set, such as the study by Gabor et al., which looked at 1,000 MRI imaging data sets. In terms of future directions, it would be worthwhile experimenting with simpler architectures similar to the ones by Birnbaum and Gabor et al. Furthermore, there is possible to use transfer learning to overcome the limited training data. Alternatively, there should be concerted efforts to generate a database similar to the ADNI Alzheimer's database for MS data, which is publicly available, to allow for a standardized place to compare algorithms in a large enough training data set. It is worth noting, though, that Deepmedic did take over 36 hours to train, but this could be due to architectural problems, whereas Freesurfer only took 6 hours. Overall, deep learning holds much promise. However, it highlights the fact that it is limited by data. Therefore, concerted effort should be made to increase the availability of public data sets. Thank you for listening.